Maybe we should start.
Okay, I'm still muted. Now I'm not. All right. Great. So our second lecture of the day, we're back to Ben Jones, who will be telling us this is his second of two lectures about neutrino non-oscillation experiments. Okay, please take it away.
Great. Okay, thank you for coming back for more, everybody who came back for more. As I explained in my introductory lecture yesterday, I decided to interpret neutrino non-oscillation experiments as being that I could kind of talk about whatever subset of those that I wanted. And I decided to talk specifically about experimental tests of Majorana neutrinos so that we could go into some depth on that topic rather than reviewing lots of different things. And we pretty much stuck to the schedule that I outlined yesterday. And I'll quickly review what we talked about before going on with today's material. But we talked about Majorana neutrinos briefly. We constructed a naive thought experiment for how we might test for Majorana neutrinos, and then quickly realized that that thought experiment actually could be manipulated into being neutrinoless double beta decay searches, which is the most prevalent way of searching for Majorana neutrinos today. And then briefly, we started talking about experimental approaches to this question. So today I plan to jump off here, talking about the experimental approaches, and then dig into some detail about the predictions of the light Majorana neutrino exchange mechanism for neutrinoless double beta decay. And if there's time, maybe talk a little bit about other methods for searching for Majorana neutrinos. So just to review yesterday's material quickly for you. We talked first of all about what a Majorana spinner is. This is obviously something you're being taught in other lectures in this course from Andre, much better than me. But essentially, we just motivated that the neutrino may be its own antiparticle, and this is an interesting and important thing to test. Then we constructed what might be the most naive thought experiment to figure out how to test for this, which is to run what would be effectively a standard neutrino source neutrino detection experiment like the one that discovered neutrinos in the first place, Project Poltergeist, but run it in a way where we're actually going to look for antineutrinos being produced and things that look like neutrinos interacting. And if we see something produced as an antineutrino and then eventually interacting as a neutrino, that suggests to us that the neutrino and the antineutrino, in some way, they are the same thing because the same particle has been produced as one and detected as the other. And indeed, this is an experiment that can in principle be done, can in principle work. But the problem is that the constraints imposed by the chiral structure of the weak interaction and conservation of angular momentum mean that the expected rate of this process is incredibly tiny compared to the expected rate of the standard process. And so we found from a back of envelope kind of calculation that if we try to do this particular experiment, maybe 1 in 10 to the 13 of the neutrinos would give us this kind of process, which could be considered a Majorana neutrino discovery. And unfortunately, that's such a low rate that it's inconsistent with our current experimental programs. But then we cajoled this experiment into one where both the neutrino production and the neutrino detection are happening within the same nucleus, effectively the same experiment, but done over a 1 Fermi baseline. And that gave us this process, and this process is called neutrinoless double beta decay. It's incredibly slow for the same reason that the rate of the above process is incredibly small. On the other hand, the backgrounds to this process are less severe than the backgrounds to the one above. And so this actually is a somewhat plausible way of searching for the Majorana nature of the neutrino, looking for this conversion over these nuclear scale baselines. Then we introduced what the backgrounds really are to this process. And one of the most important backgrounds is called 2-neutrino double beta decay, which is like this process above, but where the neutrino is not virtual inside the Feynman diagram, but the 2 antineutrinos are actually emitted. And this is where we're going to jump off talking today. So we have these 2 processes, one that is in principle a discovery process for Majorana neutrinos, which is a nuclear decay where an isotope with n neutrons and z protons turns into an isotope with n-2 neutrons and z + 2 neutrons and 2 electrons. If we see that, we go collect our Nobel Prize because we've discovered Majorana neutrinos. This one is the standard model process where the nuclear transition is still from nz to n-2 z + 2, But in the final state, we have both 2 electrons and 2 neutrinos. Since we can never detect the neutrinos here, they're just going to zip through the detector unless our detector is a light year in size, which it will not be. But since we can never detect these 2 neutrinos, we're always going to be experimentally focusing on either the daughter nucleus or the electrons. And the vast majority, well, all experiments that have been done to date have worked on detecting the electrons, although some of us are working on R&D to detect the daughter nucleus. But since you can only detect the electrons, the way you can tell the difference between these processes is by trying to figure out whether there's missing energy that has escaped in these invisible neutrinos. And that led us to the discussion of this spectrum, where for the boring standard model decay mode, that's this blue one, the energy is going to be shared between 2 observable electrons and 2 undetectable neutrinos. And so there's a continuum all the way from the electrons carrying none of the energy and the neutrinos carrying it all down here, all the way up to the random case where the electrons carry all the energy and the neutrinos carry none up in this long tail. Whereas the really interesting process, neutrino-less double beta decay, the electrons carry all the energy, and so you get this localized spike, which is very tightly localized around the Q value, and the Q value is whatever the mass difference is between those 2 nuclei, because that's the energy that's driving these decays. So in the case of xenon decaying to barium, which is one I'll be using as an example throughout these lectures, the Q value is 2.4 MeV. So in the case of the neutrino-less mode, all of that energy goes into a single spike in detectable energy here. And so to tell the difference between the process of interest, this one, neutrino-less double beta decay, and the standard model background, which is 1,000,000 times more prevalent, what you have to be able to do is measure the energy in these electrons with enough precision that you can draw a window thin enough that you don't integrate a bunch of activity from this peak. Let's see, I have a question in the Slack channel. Is it possible that electrons in neutrino-less double beta decay scatter with other nuclei and then lose energy and thus looks like 2 new BB? Yes, so this is actually a nice question because it gets to what we're going to talk about today at the beginning of the lecture and what these experiments do. I mean, indeed, what happens is those electrons then come out and they scatter in the material. So in either neutrino-less or 2 neutrino double beta decay, you have your nucleus and then it spits out these 2 neutrinos. And these neutrinos don't just spit out into a vacuum, they immediately start, colliding with things and scattering around. And they give all their energy away through these collisions. But the way you actually measure the energy of these electrons in almost all of these experiments is in the collisions, the way they give their energy away is either that they can collide with an atom and then kick out another electron, and then this one has high energy and bounces along, continuing to collide. So they either produce a whole bunch of electrons, or the other thing that they can do is collide with an atom and then send it into an excited state, which emits a photon. So there's a whole bunch of photons emitted as well. And the final place the energy can go is into recoils of these atoms, because the atoms have somehow been heated. The recoil themselves carries some energy. So the energy is partitioned between sort of shaking atoms, photons, and electrons. And all of these neutrino-less double beta decay experiments, their goal is to measure some of these channels, either the charge or the light or the heat, and use that to infer how much energy the electron had. So indeed, the electron emitted in this decay does give its energy away to its surroundings, and then the goal of the experimentalist is to collect that energy from the surroundings. Okay, so that happens for both processes. Does that address your question, or were you getting at something slightly different that I didn't touch on? You can just let me know that in this chat. Okay, very good. Thank you. Good. And so, yeah, I mean, obviously the quanta involved here, generally these are electrons or charge. These are photons or light. I know you can't really read my writing, but I'm writing it as I say it. And these are phonons or heat. And all of the experiments are looking at some combination of photons, phonons, and electrons for their signals. Okay, very good. So we know then that one thing that a really sensitive neutrinoless double beta decay experiment has to be able to do is reconstruct the energy well enough to not get contamination from this blue swathe of 2 neutrino double beta decay background. And in practice, to reject this background to levels that are really negligible, and the negligible here I define as 0.1 counts per ton per year in the ROI, and today I'll explain where that number comes from. You need to achieve an energy resolution of at least as good as 2% full width half max. So then we finished yesterday on this plot, which is showing the energy resolutions achievable by different technologies today. And I divided them into 3 categories. I divided them into this category, which are big experiments, this category, which are precise energy measurements, and this category, which are somewhere in between. And so this top category are clearly above this line, where they're going to be limited by 2 neutrino double beta decay backgrounds. And indeed, we looked at this one, which is presently the world's leading limit on neutrinoless double beta decay, comes from this experiment. And indeed, when we looked at the background budget, we found that the background is dominated by the 2 neutrino mode background. So the energy resolution of that experiment is such that it's eating into the tail of this distribution here. And that's where most of the background comes from. Now, the other experiments which are below this line, and this is where the new material for today starts. The experiments far above this line are dominated by the 2 neutrino mode background. The experiments kind of around the line, somewhere like there, have some background from the 2 neutrino mode and some background from other places. And the experiments below the line are dominated by backgrounds from other places. Okay. And so the 2 neutrino mode, the only real way that we know to get rid of that background is to detect the energy very well, because ultimately a signature of up here really does look indistinguishable from this, because it's just 2 electrons, but the electrons have a different amount of energy. So this particular background can only really be rejected by measuring the energy very precisely. Now, the other backgrounds in these experiments, though, can be rejected in other ways not to do with energy measurement. In particular, these experiments over here utilize other mechanisms for rejecting the backgrounds, which are not the 2 neutrino mode background. I mean, those other mechanisms only really become relevant when you get below this line, and then you're not dominated already by the 2 neutrino mode one. Okay. So what I want to do now briefly is talk about what those backgrounds are and where they come from. And often in a normal sort of colloquium or seminar talk, I would spend a lot of time on ways to reject these backgrounds. My suspicion is that as theorists, you're probably not so interested in those details, so I'll review it quite quickly. And then I'm going to get back onto some more theoretical topics related to the predictions of the rates of double beta decay. But okay, so the backgrounds, once you get rid of the 2 neutrino mode through energy resolution, you become dominated by other backgrounds which come from basically radioactivity in materials. And so these are 2 examples of background models that I've taken from running experiments. So this is a background model from the Nexo experiment, or is it EXO 200? It might be EXO 200. Anyway, this is a liquid xenon experiment. Let me say that at least. This is the background model from a liquid xenon experiment. This is the background model from the next experiment, which is gaseous xenon. And you can see that actually their backgrounds are dominated by mostly the same things. This red thing here is elements from the uranium-238 decay chain. And the uranium-238 decay chain is shown on the right here. So all materials contain some amount of uranium and thorium, and uranium decays through an alpha decay here to this thorium isotope, and then through a beta decay, an alpha decay. And gradually there are just decays all the way down through this chain, emitting betas and alphas and gammas. And then in this chain, there's a couple of especially problematic ones for double beta decay. In particular, this one, bismuth 214, is especially annoying. And the reason it's especially annoying is that this decay, this beta decay here, has an energy which is quite similar to our Q value, our region of interest. And it means that when this decay happens, it sort of adds contamination at about the right energy in our spectrum. So if you look at the spectra here, this particular decay gives us a sort of a peak, which is quite close up here, okay? And so that means that this stuff being in the materials of the detector presents us with a challenging situation. Now, of course, all these other decays are like throwing random charged particles into the detector as well and putting energy into the system. But for the most part, these ones have either the wrong energy or go too slowly, or maybe they make alpha particles, which we don't distinguish, which we're able to distinguish from beta particles. Really, there's only a limited number of these decays which are truly a problem. This is certainly one of them, bismuth-214. There's another one which comes from thallium-208, which I think is not part of this decay chain. I think that one comes from the thorium decay chain. But thallium-208 is also a problem by virtue of having a similar energy to the process we're looking for. And you see that in the case of this experiment on the left, this bismuth-214 is the most largest part of the background. It's this red. Bismuth-214 is a major culprit over here as well in the blue. And then there's other isotopes like this is the thallium-208, I think, they're from the thorium decay chain. That also shows up over here, this one. And remember, we're looking for backgrounds around this place, 2.4 MeV Q value, okay? So essentially what you have to do to do any of these experiments is get very, very clean detector materials. And you have to not only buy them clean, but keep them clean when you're building the experiment, and control very well the trace amounts of metals that are in those, in the steels and so on. I'm not going to go into great technical detail about this because there are people who literally spend their entire careers looking for ways to make and keep materials clean for these experiments. One thing I will do is show maybe the funnest example of the lengths people go to get clean materials here. So this is the Quarry experiment, which is the one based on tellurium dioxide bolometers. So this experiment here is the business end in here. This that I'm circling with my pen is the array of crystals. And this has to be inside a cryostat, which is reduced in temperature with a dilution refrigerator to keep it very cold, so they can measure these very small amounts of heat produced. And like all of these detectors, it's kind of like an onion with the layers of the onion skin becoming increasingly clean materials as you go into the middle, because the first thing you do is surround it with a load of copper, because copper is the cleanest sort of commercially available material that we know about. But the copper itself has some backgrounds from uranium and thorium. And so you have this thick layer of copper, which takes away the backgrounds from all the steel and everything outside of this. And then as you move towards the middle, you move through cleaner and cleaner materials. And the very, very middle layer here is something called Roman lead. And Roman lead is an especially interesting material, which only collaborations which are based in Italy have access to. What Roman lead is, in fact, this is a picture of them acquiring Roman lead. Roman lead is actually the ballast that was part of an ancient Roman galleon that sank in the Mediterranean Sea 2,000 years ago. And this lead, because it sank with that ship, has been underwater and protected from the radioactivity of cosmic rays for 2,000 years. And so inside this lead, any of the isotopes which have a half-life of less than 2,000 years have decayed away. They've not been activated by cosmic activation. So this collaboration actually sent divers to go and retrieve the ballast from this Roman galleon, melt it down, and then use it as the inner shield of their neutrinoless double beta decay experiment, because it was the cleanest available metal that could be found. As I say, this is only a valid approach if you live in Italy, I think. And even then, it's arguable how large. Arguably, it can't be scaled to very large scales, but it's a fun example of the lengths people go to get clean materials here. Somebody made a comment, damn. Yes, very, very good, I agree. Okay, anyway, so backgrounds, that the first thing you need to do is get the detector very clean so you don't have many of them. Then the next thing that you can do is, once you've got the detector as clean as you can find ways other than energy resolution to try and get rid of them. And so the reason I separated in our picture of the experiments here into these three categories is that these experiments up here are dominated by 2 neutrino modes. So it doesn't really matter what you do to reject the backgrounds. The energy resolution will limit you for the 2 neutrino mode. These ones with the precise energy measurements, basically the only thing they measure is energy extremely precisely. And so you hack away at the backgrounds by choosing a finer and finer energy region, and then that's whatever background falls in your energy range is your background. So that's kind of the working principle of these experiments. And these ones up here are in between because they play other tricks. They both measure the energy and they also use other techniques to reject these other backgrounds. So in the case of NEXT, at least, the 2 neutrino mode is really irrelevant. And all of the backgrounds that are relevant come from these radioactive materials. And so you can use other techniques than energy resolution to reject them. So to give you an idea of what some of those techniques look like, one of the things that the NEXT experiment does is, because it's a gas detector, it actually images the events. So remember I told you a minute ago about this process by which the electrons wander around depositing their charge, depositing their energy, so produce all these ionization electrons from the decay. Now, in a gaseous detector, these go non-trivially far. These go a few centimeters. And not only that, but as these electrons go, they're losing energy, and so they're becoming more highly ionizing. So eventually what you get is like a lot more electrons at the track end up here. So you end up with kind of two blobs at the end. And this is an example of what an event with 2 electrons emitted looks like with 2 blobs at the end. Now the backgrounds here are primarily gamma ray interactions from these materials. So the gamma ray interaction, instead of looking like this, looks like there's a gamma ray coming in, it kicks an electron off, and then it scatters away. And so this interaction produces a single electron. That single electron then wanders around and deposits all its charge deposits all its energy into other electrons. And in this case, you only get a single, what we call a blob at the end. And so this is what the background event looks like. And so by telling the difference between these in the detector, we can reject the radioactivity backgrounds even more than we can do with the energy resolution alone. There's another technique as well, which is used by the liquid xenon as well as the gas xenon. This is a plot from the liquid xenon experiments. So this relies on the fact, this technique is called single site versus multi-site discrimination. This technique relies on the fact that if you have one of these double beta decay events, you'll have some sort of localized charge deposit. In liquid xenon, this is actually very tiny, maybe millimeters in size, this charge deposit, and they image it. But if you have enough detector material, then in the case of the gamma ray backgrounds, what quite frequently happens is the gamma ray can come in and then scatter again, and then before it leaves. So you actually get sort of 2 electrons in the detector. So when you get 2 electrons, this is called a multi-site event. When you get when you get 2 deposits of charge, spatially separate from each other, this is called a multi-site event. When you get 1 charge deposit in one place, it's called a single site event. And the signal obviously is in this category. So they separate their sample into single sites and multi-sites. And it's obviously more complicated than this, and people use all kind of techniques like deep neural networks and machine learning and things to really maximize the capability of these imaging detectors. That's not something I really am going to talk about today, but this is just meant to be an illustration of this idea that when you're in this regime, you've already basically suppressed the 2 neutrino mode background to the point it doesn't matter, and then you can use other techniques to reject the other kinds of backgrounds in the experiments. So, okay, so when all is said and done, the backgrounds of all these experiments, oops, sorry, excuse me, moving my screen in a way I didn't want to. These are the background rates that have been demonstrated by these various experiments so far, and this includes both the 2 neutrino mode backgrounds and the radioactive backgrounds. And you see that by far the most sensitive that have been done so far in terms of achievable background index are these precision energy measurement kind of detectors. They're achieving background indices something like 2 counts per ton per year in the region of interest. For them, the 2 neutrino double beta decay background is irrelevant. They're completely affected. They're completely dominated by the radioactive background. The very large detectors have relatively poor background indices because they're still limited by the 2 neutrino mode. And then there's a possibility with the imaging detectors as well to reach this, this low level of background, which is going to be demonstrated soon, we think. So again on this chart, and this is what I want to talk about next, again on this chart, you see this goal marked of 0.1 counts per ton per year per region of interest. And it says NSAC goal. NSAC is the Nuclear Science Advisory Committee, which is a body that sort of advises the field of double beta decay. But this is the same goal that I marked on this energy resolution plot here, where you want to reject that background to this level. I mean, really, whatever your backgrounds are, to have a truly sensitive search, you want to get to this line. And unfortunately, even though there are very powerful experiments that exist, all of them, even the best ones, are still factors of like 20 to 40 away from this line. And the worst ones are factors of like 1,000 away from this line. So the technologies still need development to be as sensitive as they can be, clearly. But then what I want to do now is explain where this number comes from, because it sounds like an arbitrary thing I just made up. But where it comes from consideration of how the sensitivity of an experiment grows over time. And so what I'm about to talk about now actually applies to any low background experiment, anything where you're looking for a rare process over a low background. This general line of argument will apply to, but it's especially relevant today in neutrinoless double beta decay. So this plot shows you, for a given experiment, what the half-life sensitivity will be. This is the 3 sigma discovery limit, which is just a way of characterizing a sensitivity. And so you see these half-lives that we're looking to reach are in the sort of 10 to the 26, 10 to the 27 years regime, which is, as I mentioned to you before, what you're looking for with double beta decay. So this plot shows you the expected discovery reach as a function of exposure, and exposure is measured in ton years. So if you want to have a more sensitive experiment, you can either run it for longer or make more of it, right? They're the same thing, basically. You can run 10 tons for 1 year or 1 ton for 10 years. What really matters is the exposure of the experiment. Now, in an ideal world where your experiment is perfect, which of course nobody is, you would follow this red line, the background free line, okay, this one that's running up the diagonal here. And what you notice about this line is essentially linear, right? It's essentially a first order power law, okay? Proportional is the word I was looking for. So we can just check ourselves that that's the case. So if I go here, okay, and go up here. Those aren't straight lines, but imagine they're straight lines. This is basically a linear relationship, right? We multiply the exposure by 10, we increase the sensitivity by 10. And the reason for this is that in a background-free experiment, if you see one event, you've made a discovery. Because if there's no possible background that you can ever imagine, you've done all your radio purity and screening, and you've got this solid gold plated event, and there's no way a background can fake it. You see one, you claim a discovery. And so that means that if you want to have sensitivity to a half-life of, say, 10 to the 26 years, you just need to wait for long enough that you expect 1 decay to go in your detector, okay? And so if you wait 10 times as long, then an event which is 10 times slower is likely to go in your detector. So that's why in the background free regime, you follow this linear relationship, okay? And obviously you can't do better than background free. That's as fast as you could ever hope to make a discovery following that line. Now, these curves, which are not background free, follow what my friends in the IceCube collaboration would call a broken power law, okay? And a broken power law means that down here, like let's take this one, for example. The broken power law means that down here, we're following a linear slope. So this means that the half-life sensitivity here is proportional to exposure. Whereas up here, we're following a square root relationship. So here, t half is proportional to square root e. And somewhere in the middle, it breaks. Okay? And as I said, this general conclusion is going to be true of all low background experiments. So somewhere there's a break in the power law. And so what's happening here is that down in this regime, you have some level of background in this experiment, 0.1 counts per ROI per ton per year. When you have very little exposure in this apparatus, when you've only run this for something like 1/100th of a ton year, if your expected background level would be 0.1 per ton year, then the expected amount of background that you would have collected here would be like 10 to the minus 3 events. That means that if you see an event, it's at least at the 90% confidence or the 3 sigma confidence level, if you see an event, it's definitely not going to be from background because you're expected, or not definitely, but it's at 3 sigma confidence level, not going to be from background because your expected background rate is so low, you're effectively in a background free regime. Like you see an event, it's almost certainly a signal event at the relevant confidence level. So this experiment is behaving basically like it's background free in this part of the curve. On the other hand, when you get to the regime where there's a non-trivially large chance of having a background event in this exposure, so for example, when we reach 10 ton years of exposure here, this means that your expected rate of background now is something like 1 event. So that means that when you see a signal event, you can't suddenly just send it straight to nature and say, I found the 1 event I was looking for over a background of 0. The best you can say is, I saw 1 event and I expected 1 event. And so this is consistent with my background expectations, or maybe if I'm lucky, it's a signal event. And so when you move into this regime, you're in a statistical discovery regime. So in the statistical discovery regime, what you have is some predicted background. So some predicted, this is the, maybe this is energy spectrum versus number of events. So you have some expected background spectrum, and then there's some signal you're looking for on the top, okay? And so the way you characterize whether or not you have a significant observation here is you ask, what is the probability that my background could have fluctuated up to be as large as that signal? And if you have Poissonian regime, which we generally do in these experiments, then the background rate is going to be something like the mean amount of background plus or minus square root of the background. Okay. So the number of sigma that you have up here is something like signal over square root background. Okay. And in this experiment, both signal and background grow proportionally to exposure, because if you run twice as long, you collect twice as much signal and also twice as much background. So both of these are proportional to exposure. Signal is proportional to exposure, background is proportional to exposure. And so the rate of accumulation here scales like square root of exposure, okay? And so it's this transition from the background free region on this side to the statistical region on this side is what causes the break in this power law. And the more background you have, the further left the break occurs. Okay, so this is pretty important actually, and this is a key way of understanding sensitivities of experiments looking for rare processes, because there's a really big difference between your sensitivity growing like time and your sensitivity growing like square root time. Okay, if you're growing like square root time, it's actually very challenging to make major steps forward. I mean, if you're growing like square root time, then to have a factor of 2 increase in your sensitivity, you have to run for 4 times as long. Okay. And so the experiments are really powerful when up to the region of interesting parameter space, they're riding this background free curve as long as possible. Okay. So this pink band, I'll explain what this is in a minute. That's what the second half of this lecture is, but consider this pink band interesting parameter space for neutrinoless double beta decay for the time being. The background free experiment can get there if it's maybe 1 ton in size. If it's 1 ton in size, then I can interpret this x-axis as just being years. Okay, so if it's 1 ton in size, looks like it could get there in a couple of months if it was background free. Right? On the other hand, if it has even this very low background index, the one I said is the target for the field, it no longer takes 6 months to get to the end of the side of this band. It takes like 10 years, right? If it's got a background index of 1 count per ton per year in the region of interest, it'll take 100 years. And if it's got a background index of 10 counts in the region of interest, it'll take 1,000 years. And so these are pretty substantial differences, right? Even though these are very small levels of background, the difference between an experiment taking 10 years, which is a plausible timescale, and 1,000 years is major, right? 1,000-year experiment is one we will never see the end of. So just to remind you, this one that will take 1,000 years to cross the interesting parameter space has 10 counts of background in the region of interest per ton per year. Now, it's a little bit harrowing then to go back to this picture and look at where we are right now in the field. You see that the target was here, no one is there. This is taking a couple of years, right? The existing like large experiments are somewhere between 1 and 10 counts. So that was somewhere between 10 and 100 years. And the background indices of these kind of technologies are in the regime where it will take 1,000 years for them to be sensitive for those demonstrated technologies. And so technological innovation is vital for this field. There are ways that people are developing to get across this line. And we hope there will be continued R&D that does allow them to cross it. And that's something that motivates many of us in our R&D projects right now, is achieving that. Okay, so that is the end of this particular section on experiments and sensitivities. And maybe I'll just pause and see if there are a couple of questions now before I go on to the other section, which is kind of a distinct discussion. Does anyone have any questions for me right now? Okay, looks like no, but I'll take questions at the end on all the material, so no worries. Okay, so now I don't know how far through this material I'll get. How do you get 10 to the 26 years? Is it dependent on the model? Yes, and that's what I'm going to talk about now. So thank you very much. What we talked about with our measurement before, where we shrank that sort of thought experiment down into the scale of a nucleus, is one particular way of driving neutrinoless double beta decay, and it's the most standard way people think about it. It's called light Majorana neutrino exchange, and this is the Feynman diagram for it on the top left here. Okay, but you can drive neutrinoless double beta decay with actually many different kinds of beyond standard model physics, in fact. Here are some examples. This is from a slide that I stole from Andrea Giuliani, who's a Cupid spokesperson, from his talk at Neutrino 2018. You are probably people who know more about these things than I do, like supersymmetry and Kluser-Klein and right-handed currents and so on. But there's a large number of different mechanisms that can drive this decay. And there's actually something called the Schechter-Valley theorem, which I think maybe Andre will talk about in his coming lectures. But the Schechter-Valley theorem tells you that no matter which one of these that you see, the neutrino is a Majorana particle. And that's because whichever one of these processes you have, you can put it inside a loop diagram for a correction to the neutrino mass, and it will cause an effective Majorana component to the neutrino mass and generate a Majorana neutrino. And I'm not going to really discuss or prove that theorem here, but I want you to be aware that no matter what mechanism drives neutrinoless double beta decay, if you see neutrinoless double beta decay, the neutrino is necessarily a Majorana fermion. And so this particular mechanism, the standard in inverted commas one, drives a lot of the ways that people talk about and think about the field. Personally, I have mixed feelings about talking about it in these terms. Because generally speaking, there are many reasons to believe there is new high-scale physics that will show up in some effective field theory way and can introduce these corrections to that can generate double beta decay. And we certainly shouldn't be limited in our scope of experiments that we try and do only by thinking about this mechanism. And sometimes people do use it in that way. But nevertheless, because this is the way that people talk about double beta decay, I wanted to spend some time today telling you a little bit about what that mechanism predicts for observability of double beta decay. Okay, so I'm going to start again. I guess we've got the Feynman diagram here, but I'm going to draw it in a slightly different way for this discussion, more like what I drew it in the last lecture. So what I'm going to do is collapse these W's here, or maybe a different color would be better there. Collapse these W's here down into kind of Fermi theory vertices, because the energies here are so low that the W is very far from its mass shell. A Fermi theory type approach is a perfectly reasonable thing to do. So we're going to have something that actually looks like this for our diagram. Okay, these are the electrons, and this is the neutrino, and then this solid black thing is the nucleus. So there's NZ, there's an intermediate state with n-1, z-1, and then there's n-2, z+1, and n-2, z+2 over here. So this is the diagram we're going to analyze here. Okay, and so these are there's each of these vertices there's a G Fermi and a VUD, because this is an up quark turning into a down quark in the end in each of these vertices. Okay, so there's one at each of those. Okay. When we're trying to calculate the rate of this, we can't just like start with the standard model Lagrangian and go from there, from SU2 and SU3 and so on. And the reason we can't just start from the standard model Lagrangian is we don't even know analytically how to build protons from that Lagrangian, let alone how to build nuclei. And so we have to start from something which is a little more phenomenological than that. And where we start from actually is the Hamiltonian, the effective Hamiltonian that drives this decay. By the way, this treatment I'm giving here is going to certainly omit some important steps. I'm going to skip some of the math and brush some details under the carpet because I just want to give you a flavor of the physics here. But if you want to see more details, I'm following the treatment basically from two places, from the book Fukugita and Yanagita, which is a famous neutrino physics book. I think it's called the Massive Neutrinos in Physics or Astrophysics or something like that. So that's a book. And then there's an article by Haxton and Stevenson. And in the lecture notes, I'll give you, you can find the references to these and you can fill in the mathematical and formal gaps that I'm going to leave here. But okay, so where we start from then is this effective Hamiltonian, which is going to have the following form. So we've got a square root 2, because why not, G Fermi VUD squared. So that's these factors of these two vertices. And then we're just going to have phenomenological currents, basically. There's currents here, right here. So four currents come next. And the currents are E, gamma U, 1 minus gamma 5, nu. These are weak interactions, so they have these V minus A structures. So we'll do the leptonic currents first. 1 minus gamma 5. Let's see. And then P, gamma mu. 1 minus, so this is supposed to be a nu, 1 minus GA, gamma 5, and then I'm going to run out of space for the last one, but it's P bar, gamma nu, 1 minus GA, gamma 5, N. Okay, so this is the Hamiltonian that's going to drive the thing. And so it has the form that you can sort of intuit from looking at this diagram up here. The first thing I want to address actually is in the form of these currents. These up here in the leptonic currents have the expected V minus A vertices, right, from the weak interaction. Now, interestingly, these ones are the nuclear vertices. These have not V minus A, but V minus GAA. Okay, and that's kind of strange because this is a weak interaction, right? Like, why is it not just V minus A? And actually, the reason I'm bringing this up now, rather than just saying, oh, it's a thing, don't worry about it, is this GA is a thing that people talk about a lot right now. So I thought it was important to tell you something about this GA that shows up for some reason in this Lagrangian. I mean, in this Hamiltonian. So essentially what this GA is so if we had just a nucleon decaying in vacuum, not inside a nucleus, then what we would have is a process that looks something like, this. Okay, this is a beta decay, neutron, we'll just call it capital N for nucleon for the time being. So and then we'd have a neutrino and an electron. Okay. So this is what we would have in the case of a nucleon in vacuum. And so this current here would just be V minus A form. Now, what in the situation we're really in, though, we're actually inside a dense nucleus of strongly interacting nucleons. And so the nucleons are in fact so dense and so strongly interacting that other nucleons can interfere with this while this process is ongoing. And so there are diagrams that cannot be neglected, which look something like this maybe, where there's another nucleon that's traveling along, which spits out a pion, and then that pion interferes somehow at this decay vertex. Okay. And there are other examples as well where there's not even a pion involved. Another example of one of these corrections. Another example of one of these corrections is such that another nucleon itself, in fact, interferes with this decay somehow. And this only happens inside the nucleus, where you're in this strongly interacting soup of nucleons. It's like the nucleon themselves can't be discovered, can't be thought of as really truly independent degrees of freedom. They're so strongly coupled to their surroundings. And what this does is it changes the effective charges at the vertices. And so it messes with these currents. Now, the obvious question then is, okay, well, we accept then that nuclear physics is complicated. I thought even in vacuum, we already would have GA, since the nucleon is not a point-like particle. Yes, okay, that's right. The pure nucleon in vacuum itself will also have GA, that's right. But the point is that there are these corrections that interfere with its value from strong interaction physics. Okay, you are right, the nucleon itself has a GA as well. But anyway, so that, yeah, there are these corrections which occur here. But the obvious question then is why do they only correct this? Oops, not that piece. Yeah, why do they only correct this piece and not this piece? Why do they only correct the axial current, not the vector current? And actually, this comes from something called the conserved vector current hypothesis, or CVC. So the conserved vector current hypothesis is actually a hypothesis that significantly predates the standard model. It was invented, I think, by Feynman, if I remember right, and a few other people simultaneously to explain weak interactions before people understood that weak interactions were mediated by W bosons. And the conserved vector current hypothesis relies on a line of argumentation that is the following. So if we imagine that the protons and neutrons are just aspects of some particle called a nucleon, and they're distinguished by isospin, we can make an isospin vector, right, which is like psi is Pn. Okay? So this is a nucleon has some quantum state in this particular Hilbert space, and so a proton is 1, 0, and a neutron is 0, 1, and so this has T3 of +1, and this has T3 of -1, where the T's are the isospin matrices, which are the Pauli matrices, basically. So in this picture, if you think about how the electromagnetic current couples to the nucleons, the electromagnetic current obviously couples to protons because they're charged. So the electromagnetic current for protons looks like this. Okay. But the electromagnetic current doesn't couple to neutrons. There's a 0 here because the neutrons are non-charged. And so if we arrange these protons and neutrons into an isospin vector like this, we call this the N for the nucleon, okay, then the electromagnetic current here is going to have the form of N 1 plus tau 3 N. Okay, because 1 plus tau 3 is like 1, 0, 0, 1 plus 0, 1. Oops, no, sorry. Plus 1, 0, 0 minus 1. Okay, so that will give us the one that will pick out only the proton. Okay, so the electromagnetic current, because it only couples to the proton, couples to this particular mixture of this particular isospin operator. And so what this actually is then can be written as a current, which is coupling to isoscalar plus the third component of a vector isospin current, T3. And in principle, you can imagine currents instead of involving T3 that involve tau1 and tau3 involve tau1 and tau2. Now the weak current couples more complicatedly. The weak current has a vector part and an axial part, as we know. So the weak current has couples to the nucleon, and it's got a vector part, gamma u plus gamma u gamma 5. Okay, and so we can think of this as a vector current plus an axial vector current. Okay, and now I want to be careful here because the word vector can get confusing in these situations. This vector means 4 vector, whereas this vector means vector in isospin space. Okay, so maybe I'll call this isovector. It gets very confusing in the literature when people mix these up, and I'm sorry, so I did it subconsciously here as well. But okay, this is a vector current plus an axial vector current. This is an isoscalar current plus an isovector current up here. Now the vector part of the weak current has the form, from W boson interactions, we're generally going to be converting protons into neutrons or vice versa. So we have to be applying isospin raising or lowering operators in these currents. So the vector part of the weak current, the vector part of the weak current generally is going to have the form n bar tau1 plus or minus I tau2 n. Okay, because always this current is going to be coupling protons sorry, and then there's the matrix here. This is always going to be coupling protons to neutrons or neutrons to protons because the weak bosons change the isospin. So this weak current then can be expressed as the first component of an isovector plus or minus I times the second component of an isovector. So interestingly, this weak current is related by a rotation in isospin space to this electromagnetic current, which is a sort of unusual relationship between them that was understood sort of as the standard model was being developed. So now the conserved vector current hypothesis says the following. The conserved vector current hypothesis says that these 3 contributions, this one, and this one, form a vector in isospin space, and each element of that vector is conserved. So basically it says that n bar tau gamma mu n equals 0. This is the CVC hypothesis. And this actually is a prediction of the standard model when you eventually work out the details of it. But essentially what this means is there's a symmetry relationship, isospin symmetry, which is relating the strength of the weak vector current to the electromagnetic vector current. Okay. And what that means is that any of these nuclear processes that are interfering with the couplings in here, any of these things, if they won't interfere with the electromagnetic couplings, then they also won't interfere with the vector part of the weak couplings, as long as isospin is a good symmetry. And to the extent that the mass of the up quark and down quark are different by a very small number, then isospin here is a good symmetry. And so that means that because of this symmetry, this number is protected. So this, because it's related to the electromagnetic current, and the electromagnetic current is not interfered with by these corrections, is fixed at 1. And this one is modified by the corrections because it's not protected by that symmetry. So that's a very short introduction to GA and why it's a number that people care about, and it will show up ultimately in the decay rates and is a source of ongoing theoretical research at the moment as to what its value really should be. Okay, so that was a little aside, but now I want to move on with calculating the rate from light neutrino exchange, and I'm probably going to have to skip some of my material because we're going to run out of time, but such is life. Okay. So to get a matrix element, which is what we really want from this, what we're going to do is we're going to jam wave functions on both sides of this Hamiltonian, like this. a wave function there, and a wave function there, which is going to be a wave function of the nucleus and the final state leptons. And because we're looking at the process where the neutrinos from both these two vertices are connected, we're going to make a contraction of this. Okay. And so skipping a couple of the technical steps, but hopefully you can see at least schematically how this will come out, we'll end up with a matrix element which looks like -2 G Fermi squared VUD squared. And so, okay, so the next steps, I'll write it all down and then I'll talk about what all the pieces are. So sum over n d4k 2 pi to the 4. Give me a minute to write it and then I'll talk again. Gamma mu. Okay. So I'll start talking before I finish. So little n here is the intermediate state of the nucleus. So remember in the middle, there was a nucleus with one less proton, one less neutron and one more proton. That state, in fact, is not uniquely defined. There are various excited states that you can go into of that intermediate nucleus. Remember, it's a nucleus which is actually energetically forbidden to exist, so it's virtual in some sense because of that pairing interaction. But which excited state you go into is not itself uniquely defined. And so you have to sum over n, these intermediate final states of the process. Here, sum over those, okay? That's what this sum is. K is the energy of the neutrino, which is in a loop. So you have to integrate over the momentum, over the form momentum in that loop. There's the form momentum integral. We have then spinors for the, oh, I missed a U somewhere. This P1 and P2, P2 is over here. U of P1 and P2 are the spinors representing the emitted electrons. We have weak vertices here. This is the propagator. Well, this and this exponential actually both come from the propagator of the neutrino in the middle. So if you look at Fukugita and Yanagita, they explain how to get the propagator for Majorana neutrinos. It comes out looking basically the same as the propagator for Dirac neutrinos, although it didn't have to, but they show that it does. And that's what this is. We have another weak vertex. This is part of the propagator. And then these are the currents from the nucleons. So what we've done here is we've taken, because we jammed this Hamiltonian between two wave functions, these operators for protons and neutrons have been applied to those wave functions. And so now we have nuclei here, right? And the currents are between nuclei, okay? So again, we have that n that we're summing over in the intermediate state and an energy conserving delta function. So those are all the ingredients. And so this can be written in a slightly more compact form, which is going to make life easier for us in the following way. VD squared, sum over intermediate states, leptonic tensor, which depends on the intermediate n, hadronic tensor, which depends on the intermediate n. Okay. And so this is a sort of familiar way of writing a matrix element that decomposes the leptonic and hadronic systems. Now, the hadronic piece or the nuclear piece is always going to be a nightmare for us because it's going to involve details of the nuclear wave functions. It's got this nasty coupling, the GA, and so on. This is always going to be a problem. This, on the other hand, the leptonic one, should be tractable, and we can get some information about this process from understanding the behavior of this leptonic piece of the tensor. So the leptonic piece, if I pull it out from this expression, has the form d4k over 2 pi to the 4 u p1 1 minus gamma 5 over 2 gamma mu k slash mu plus m mu over k mu squared minus m mu squared gamma nu 1 minus gamma 5 over 2 u of p2 e to the minus e to the I k nu r. Okay, so this is the leptonic piece. So one of the things I want to do first of all is watch where the m nus are, because remember we argued last time that, but based on our analogy with the previous experiment, right, this matrix element is supposed to come out proportional to m. So the rate comes out proportional to m squared, right? That was because we had to pick out the wrong helicity piece of the wave function here, and that was suppressed by a factor of m over e. Now, down here, where does the m show up? It shows up there in the denominator, although that's probably going to end up being irrelevant because this k is much larger. The momentum in that loop is generally much larger than the neutrino mass. So with reasonable confidence, that's not going to be too important. It shows up here, and then there's this k here, okay? So it had better be then, if our intuition based on that argument is right, that for some reason this k disappears, which this comes in the propagator of a fermion, and this m is all that's left, so we have a tensor which is proportional to m. Indeed, that is what happens, and the reason that happens is you can think about commuting these projectors along here. So remember, when you commute a projector across a gamma matrix like this, you flip the sign of the gamma 5. Okay, because these anti-commute, whereas it commutes with 1. And so if you take this 1 minus gamma 5 over 2, you commute it one step, it becomes 1 plus gamma 5 over 2. If you commute it across the k with a slash, it becomes minus again. And then over here, it becomes plus again. And then you'll have a left projector hitting a right projector, which will kill each other. So that means that this term with the k will be annihilated by chirality considerations. On the other hand, this term with the m, you'll commute once, and then obviously it commutes with the m because it's just a scalar. You'll commute twice, so you'll have 1 minus gamma 5 over 2, 1 minus gamma 5 over 2 again, and you'll just have the one projector. It's like p left gives you p left. So that means then that we can get rid of this. Okay, and we can also get rid of one of these because they're both doing the same thing, essentially. And that's made our life simpler. And in fact, it's already pulled out one of our expectations that this tensor is proportional to the mass of the neutrino. So obviously, if the mass of the neutrino is 0, the rate of this process is 0, as we would expect it to be. And the rate of the process is going to come out proportional to the mass squared. Okay, so that's a nice step. Okay, there's a few more I have to be judicious about because I've got 10 minutes left, I think. So I have to be judicious about what I'm going to skip material-wise now. So I think I'm going to skip a few steps of manipulation here and just tell you that this can eventually be cajoled into the following form. The leptonic tensor becomes the mass of the neutrino times the metric times a d4k. All the steps in between here are in the lecture notes that I'll circulate, so you can follow them if you want to. There's u squared, and then there's a spinner for the first electron, minus gamma 5 over 2, second electron, e to the ikr. Okay, so these energies in here, in this denominator, this just comes from substituting energy momentum conservation in up here, basically. These represent the initial energy of the first nucleon. So initial energy of nucleon. This is the intermediate nucleus energy. Nucleus. And this is the first electron. Okay. So this is okay. This is good. So we have this for the leptonic tensor. Now the hadronic tensor. There's something a bit awkward here because this depends on n, the intermediate excited state of the nucleus. This leptonic tensor. And what would be really much more convenient is if this would factorize all the way. So we've got right now that this is a sum over leptonic tensors for n and hadronic tensors for n. What would be much more convenient would be if the matrix element was just a product of a leptonic piece and a hadronic piece without that sum. And there's an approximation you can make, actually, that lets you express this in that form, and it's called the closure approximation. So the closure approximation essentially is the following approximation, which is applied to the nuclear side. The closure approximation treats the term that looks like this. So we're going to have in this expression a term that looks like the final state nucleus with a current to the intermediate state about EI minus EN minus E minus E mu. So we're going to have a term in this expression which looks like the sum over these final states, over these intermediate states, of two currents multiplied by each other with a bunch of energies on the denominator here. So you can see where that's going to come from up here, right? Summing over these. Let's use a different color of line. Summing over these. Now the closure approximation says that this expression can be significantly simplified if I were to imagine that I can treat all of these nuclear excited states as having the same energy, which is the mean energy of the excitation, okay? And so this is fundamentally, this is the closure approximation, that all of the excited states have some amount of energy, which is the mean energy of the states that are accessed. Now, if that's the case, then this n in the denominator here becomes just the mean n, and so no longer something we have to sum over, okay? I guess I can get rid of the n on it to show it's not something we're summing over anymore. What that means is that then we can bring this sum up here, okay? And we recognize that this is a complete set of states now, okay? And so that sums to 1. And so the closure approximation then lets us write this whole thing, this nasty thing, in the following way: J1, J2, and I divided by EI minus the mean energy of the excitation. Okay. And so what you notice now is that this thing here doesn't depend on the intermediate state anymore. What is the physical implication to do this? Yeah, the physical implication to do this is that if the excited states are sort of all clustered up at some relatively high energy scale, let's see. Yeah, I have to think about your question. It's basically that the excited states are all sort of clustered at some energy scale, and you're accessing them all as if they have the same energy. And in fact, you can't make this approximation for 2 neutrino double beta decay. You can only make it for neutrino-less double beta decay calculation because of the fact that the neutrinoless mode is accessing these higher excited states. So yeah, it's not entirely trivial, I suppose. But anyway, this is the approximation that allows you to decouple these two things. But okay, so you see that that this now no longer depends on the intermediate state, and so the sum up here now is going to involve that this dependence on the sum has been accounted for now inside this hadronic current, and the leptonic one no longer will depend on the energy of the intermediate state explicitly. So since I don't have a whole lot of time, then let me just continue to say that what you end up with then by making the closure approximation is a matrix element that does factorize. So the matrix element then becomes 2G Fermi squared VUD squared L mu nu H mu nu. Okay. And obviously what you usually care about here is the spin summed average matrix element, because that's what gives you the rate. So then if you take all this and square it, you get the spin summed average matrix element. The L mu nu you can manipulate using trace algebra. And again, that will be in the lecture notes if you want to take a look at that. But what you end up with then, if you square and sum this, is 4 G Fermi squared VUD to the 4. The hadronic elements are going to contract with themselves because remember this L was proportional to just the metric up here in those indices. So these are going to contract with themselves. This is going to be proportional to m nu squared, as we anticipated it had to be. And then we have 2 p1 dot p2, G Fermi to the 4, thank you. 2 p1 dot p2, 1 over 4 pi, this thing that depends on position, f of r, and f of r, given I'm running out of time, I won't write what it is. But importantly, we see that the rate depends on the mass of the neutrino squared, as we imagined. Now, the final thing I'm going to mention, and I'm just going to run 5 minutes over, is that the one thing we've neglected to mention here is that this m nu is not strictly a well-defined thing, because we know that there are, where's my Feynman diagram somewhere? We know that there are actually 3 kinds of neutrino, right? There's nu1, nu2, and nu3, and they all have different masses. So this can either be nu1, nu2, or nu3. And in fact, this matrix element is going to be the sum of diagrams for each one of those neutrinos, right? So this is going to be this for neutrino 1, plus for neutrino 2, plus for neutrino 3. And then we have to mod the whole thing and square it. So ultimately, this m squared here is actually, this thing is going to be replaced by a sum over the intermediate neutrinos there. And the sum is going to be inside before we square the matrix element here. And so what we actually end up with is this expression, but instead of m nu squared here, we have a thing called m beta squared. And m beta is defined as the sum over the mixing over the PM&S matrix elements UEI squared m nu I. Okay, and that's because the reason it has that form is because for each one of these diagrams, there's a PM&S matrix element that goes at this vertex. So it comes with 2 powers of UEI when we add it together and square it in the amplitude. Okay. So anyway, this form, this can be put through the Fermi-Golden rule to get a decay rate. And when you put it through the Fermi-Golden rule to get a decay rate, you end up with a rate that looks like this, d sigma by d cos theta dE1. E1 is the energy of the first electron, and it has the following form. I'm going to separate 3 pieces in curly brackets. G Fermi to the 4, VUD to the 4 over 16 pi to the 5, E1, E2, mod P1, mod P2. E1 and E2 and P1 and P2 refer to the 2 electrons. P1, P2 over E1, E2. So I'm going to close that curly bracket. Then the next thing is the hadronic stuff. Four pi f of r squared. And then the final curly bracket is this m beta. All that squared. Okay, so these things in these brackets generally then are factorized. So this is just an integral that you can do over kinematics. In fact, it's a little bit more complicated in practice because you have to put in the Fermi function that expresses the attraction between the electron and the nucleus as it's leaving. But nevertheless, this is basically an integral over kinematics, and this is called the phase space factor. This is all the nasty stuff to do with the nucleus, which is called the nuclear matrix element. And this is the effective Majorana mass squared. Okay. So ultimately, you end up with an expression for double beta decay that looks like gamma equals the phase space factor, the nuclear matrix element, and the effective Majorana mass squared. Okay. And so if I had more time, I would tell you about what you do with all these things. But basically, the answer is G can be evaluated just by kinematic calculations, numerical integration, basically. M is horribly complicated, and you have to go to your nuclear physics friends who have supercomputers to evaluate this. And there's an uncertainty of a factor of 2 to 4 on the values of these at the moment. And this one, you know something about from neutrino oscillation experiments because it involves a bunch of mixing angles and masses, but you don't know everything about it. But you know something of this from neutrino oscillations within some degree of uncertainty. And the famous, if you're familiar with this picture, this sort of encodes what we know about it or don't know about it from neutrino oscillation experiments. Maybe if somebody wants to ask me, I can explain this picture in the discussion session and how it relates to MNU. But okay, maybe I've run out of time, so I'll have to stop here. So thank you very much for your attention.
Hey, thank you, Ben. I see one question right away. Do you want to?
It seems this treatment doesn't consider the momentum transfer from the initial nucleon to the final nucleon. So the nucleus itself is basically, you know, at rest, like in the initial and final state, because it's enormously heavy. Like we talked about that before, that there's this the recoil into the nucleus is a very tiny amount of energy. And so I think it's true that we assume that no momentum is carried away in the final nucleus. Okay, there's another question. So how important is the hadronic matrix elements for uncertainty level? I said, yeah, I mean, the fact that here's the matrix elements. Here's the various calculations that have been done. And now if there were a real expert on this here, they would probably argue that some of them are more reliable than others, and we can't just imagine the spread in them is the uncertainty. But nevertheless, you know, in some cases, the spread is rather large. Right here, there's like almost an order of magnitude of spread in this one. But that's calcium-48. So I guess there's a big spread because no one is doing experiments with that one. So it's not a high priority. But yeah, ultimately, if you think about neutrinoless double beta decay as a discovery search where you're just probing in terms of the experimental observable, which is the half-life. Where's my sensitivities picture? Yeah, here. If you think about it as a quest to get the longest half-life, but understanding the fact that that half-life could be driven by any of these mechanisms, where are my mechanisms? Could be driven by any of these, doesn't have to be this one, then basically this nuclear matrix element uncertainty is totally irrelevant, because this nuclear matrix element uncertainty is really a statement about how fast you expect double beta decay to go if this is the mechanism. If you look at it from the other perspective, that you believe this is the mechanism and you want to address the allowed values of the parameters of the PM&S matrix and the neutrino mass, if this is the mechanism, then you care about the uncertainty in the nuclear matrix elements. Okay, otherwise the Feynman rule not only contains gamma mu, gamma 5, and 2 other operators. Okay, yes, I mean, the treatment I gave here was simplified, and I said that right from the beginning, that it's a simplified treatment. There are more terms in the nuclear matrix element tensor as well that I left out here. I was trying to give a flavor of the calculation at least. Where did the Majorana mass come from? How do I get M beta includes Majorana mass and not Dirac mass? Okay, so the M beta involves the neutrino mass. So when you talk about the Dirac mass and the Majorana mass, those are sort of objects in the unbroken theory, as I understand it. The neutrino, if there is a Majorana mass at all, the neutrino has just a mass, and its mass is Majorana, is my understanding. So this mass that shows up here is where is it? This mass that shows up here is the mass of each one of those neutrinos. Okay. And
yeah, that's right. It's the mass in the propagator.
Yeah, okay. It's the mass in the propagator, the mass of each of those neutrinos. So so yeah, you get the physical neutrino mass, and then the U is the mixing to that particular mass state.
Actually, Ben, do you have a picture of the normal hierarchy and inverted hierarchy bands with any current limits on there? Oh, I guess that's sort of a cartoon limit.
Yeah, no, I don't have it in this talk, but I can tell you where it
Yeah.
is.
Yeah. No, I guess maybe this plot tells the story. But when you look at these plots, you see the vertical line, which is the 95% cosmological limit, which Kev alluded to in his talk earlier this morning. And then you see that hashed red stripe across the top, indicative 90% experimental limit. When you see the experimental limits plotted on this, they're not lines, they're bands. And the width of that band is the nuclear hadronic matrix element uncertainty.
Precisely.
Yeah.
Indicatively, like, and maybe it's a bit wider than this, but indicatively, this is where right now the existing limit is.
Okay. Oh, it's that low. Cool. Okay. Yeah. Actually, maybe I ask a question. What's the thickness of the blue stripes? I used to know this, but I can't remember.
Right.
Is this
I'm so glad you asked.
uncertainty?
I'm so glad
Okay.
you asked, because I prepared this material to talk about and ran out of time.
Okay.
So, okay. Basically, that comes from, in fact, I'll stay on this slide. That comes from the definition of that Majorana neutrino mass. Where are my notes? Sorry, let me find my notes. So we know that this axis is m beta beta, which is, as I said, defined as the sum over UEI squared mi, like this. Okay. So this depends on the elements of the PM&S matrix and the masses of the neutrinos. And if you put in those matrix elements and evaluate what form this actually has, it's cos theta 1, 2 squared, cos theta 1, 3 squared. And then it depends on the Majorana phases as well, which are not observable in neutrino oscillations, but they're there in the PM&S matrix. M1 plus 1, 3 squared, 1, 2 squared, e to the 2i lambda 2 and 2. Oh, this is a...
Okay, yeah, cool. I forgot about the Majorana phases.
Plus sine 1, 3 squared e to the m3. So okay, so this is what it looks like when you just expand out all of the parameters that are in this matrix and put it in. Now we know some of these things from neutrino oscillation experiments, right? We know this, we know this, we know this, and we also know the mass differences. So we know that in fact we can write this in terms, we can write these two in terms of m1 plus this m1 squared plus delta m squared 1, 2. And then we can write this one as square root of m1 squared plus delta m squared 1, 3. So then if you write it this way, we know this and this as well. So what we don't know is the absolute neutrino mass, which is what's on this scale. And we don't know the Majorana phases. And the Majorana phases, varying them, moves you around in this band. And varying this one moves you this way and this way.
Okay, awesome. Okay, okay. So those are okay. There's a lot of stuff happening in the chat.
Okay, yeah, I was just going to add a comment. There's a little bit of uncertainty on this band from uncertainty in the known mixing parameters, but mostly it's the Majorana phases.
Okay, okay, fantastic. Okay.
Okay, let's go. What's going on in the chat? Let's see. Oh my goodness, so much. Okay. It seems what's happening is each neutrino propagator goes like mi over q squared. That is, okay, whoever said this is correct. The propagator, sorry, where's my mechanisms plot? Whoever said that is correct. When we do this sum, we are able to basically neglect that mass in the denominator because it's so small compared to the momentum. And so the only one that really matters is the one that shows up on the top. Where is the right line? Somewhere is the right line where I've got that mass on the top. But yeah, the only one that matters is the one that shows up on the top. No, a Dirac mass would, but then a Dirac mass would give 0 nu BB. No, so a Dirac mass will not allow you to have neutrinoless double beta decay because in the case of a Dirac fermion, you're not allowed to make this contraction. This contraction only works if the neutrino field here can annihilate the neutrino field there, and that's forbidden if the neutrino is Dirac. There's more about that in Yanagita and Fugagita that explains how the Feynman rules for Majorana neutrinos work. So I encourage you to take a look at that for more information. And then, okay, then there's people debating amongst themselves. Okay, yeah, M1 and M2 are mass eigenvalue. Yeah, M1 and M2 are the physical light neutrino masses after diagonalization.
Okay, fantastic. Yeah. Okay. So I think it looks like the questions have more or less died down a bit. Ben, are you able to drop in on the coffee break this afternoon, or do you have other commitments?
Yeah, certainly I can. What time is it?
It's at 1:30 Tassie time, so an hour and 15 minutes from now, I think.
Okay, yep, I can make it.
Okay, fantastic. Yeah, so this is the E, nu, or tau discussion rooms. Yeah, so that's the next thing up.
Do you want me in? Do you want me in any particular